All right, so let's look at question 8 from section 1.3. So we have this model for the population in China in billions as a function of time. So first thing we're asked is about the total change in population between 1993 and 2000. So we're given a reference time of 1993, which means that basically we're being asked about these two values of t. So p of 0 and p of 7. So what is p of 0? So that's 1.15 times 1.014 to the 0. So anything raised to the power of 0. Any non-zero number raised to the power of 0 is 1. So this comes out to be 1.15 billion. And when p equals 7, so let's calculate that. I get approximately 1.27 billion. Okay, so we got the two population values. What else do we have to do with them? Okay, so we need the total change. So our change in population is going to be 1.27 billion minus 1.15 billion. So that'll be 0.12 billion people. Okay, so that's the total change. So let's make a note here. This is the total change. Next, they're asking what the average rate of change is. So how do we get the average rate of change? Well, that is going to be the change in population, averaged out by the change in time. So 0.12 billion people divided by, what is our change in time? 7 years. So what does that come out to be? Actually, let's represent this another way. Actually, we'll get to. So 0.12 divided by 7. And instead of expressing this in billions, I am going to express this in millions, just to make the numbers a little bit easier to think about. So this comes out to be 0.01714 billion people per year, or if you prefer, 17.14 million people per year. So our first answer was a total change. This is going to be an average rate of change. So on average, the population is growing by 17 million people per year, give or take. So next question, is this average rate of change greater or less than the instantaneous rate of change of the population on January 1st, 2000? So we don't have, given the tools we have right now, we don't have a way to get the instantaneous rate of change of population at any one point. But we can think about this. This is an exponential function, and the way that exponential functions behave, I can use a graph to kind of illustrate this a little bit. There's some beginning value, and as we go, so we have an increasing function. But not only does the function increase, the rate at which it increases, like the instantaneous rates. Again, if we're talking about instantaneous rates of change, looking at a graph, think about what the slopes of these tangent lines look like as I go from left to right. They're all positive, but also they're getting steeper and steeper, which means the more time that passes, not only are there more people in China, but the rate at which the population grows is also going to get greater. So because of that, the average rate of change, or sorry, the instantaneous rate of change in 2000 will be larger than the average rate of change between 1993 and 2000. So let's go ahead and move on to part B. According to the model, what is the average rate of change of the population in China in the 10-year period starting in 2012? So now we're looking at a different interval. So remember our reference time of 1993. So 2012 minus 1993, that should be 19 years. And we're looking at a 10-year span. So we're looking at the interval from t equals 19 to t equals 29. So we're one on average rate of change. How do we find average rate of change? So delta P, so change in population over change in time. I want to find P of 29 minus P of 19 over 29 minus 19. So how do I find P of 29? That's going to come from our formula, 1.15 times 1.014 to 29. And P of 19 is going to come from 1.15 times 1.014 to the 19. So let's calculate each of these. So in the year 2022, the population will be about 1.72 billion. And what about in 2012? So 1.014 to the 19th times 1.15. That is going to be 1.50 billion. So our average rate of change is going to be 1.72 billion minus 1.50 billion over 10 years. So that'll be 0.22 billion over 10 years, or again, we'll do some billions and millions, 0.022 billion people per year, or 22 million people per year. So this will help us maybe give it a little more convincing of an argument for our last part of question A. So our average rate of change here is 22 billion per year over this later interval, as opposed to our average rate of change in this earlier interval, which was 17.14 million people. So hopefully this gives you is a little more convincing that when we have an exponential function like this, as our values of time get larger, our instantaneous rates of change are going to keep getting larger as well. So moving on to part C, write an expression involving limits that, if evaluated, would give the exact instantaneous rate of change of the population on today's date. Then estimate the value of this limit. Discuss how you chose. Okay, so let's answer the first sentence first. So we want an expression involving limits that would give us the exact instantaneous rate of change. So how do we find rate of change? So let's start with average rate of change. So, and by the way, today's date. So if I want to find the average rate of change, basically how am I going to do that? I'm going to find the population at some later time, subtracted by the population at some earlier time. And I need to know how far apart those times are. But this is one way we've talked about average rate of change. There's something equivalent we can also do. What if instead of thinking about two different times, I just want to think about one time? But instead of, I still want there to be some separation of time, but I'm going to call that separation of time h. So I care about what's happening now. So what's happening for some value of t. So my later time is this t plus h. My initial time is this just generic t. And how do I calculate slope or average rate of change? I have to find out how far apart those two time values are. So t plus h minus t, that really just gives me this. Denominator or numerator is pretty much unchanged, but what happens to the denominator? That is simply h. So this is an average rate of change. What's the thing that allows me to kind of bridge the gap from average rate of change to instantaneous rate of change? Well, I would love to be able to calculate the slope for very, very, very small values of h. And when I say very, very small, I'm saying I want to get as close to zero as I possibly can. So the tool that allows us to do that is the limit as, well, not as t goes to zero, but as h goes to zero. The limit as h goes to zero of this thing, population of time plus h plus the population at time t divided by h. So we wanted to do this for today's date. I am going to modify this a little bit. Instead of saying today's date, let's try to set this up for the beginning of the current year. So January 1st, 2024. So that translates to a time value of what? 2024 minus 1993 is 31 years, so t equals 31. So I want to look at this. What is the limit as h approaches zero of the population of year 31 plus some small little h separation? And by the way, I am really messing this up. Very, very important modification needs to be made here. You don't calculate slope by adding these two values together. I want to know how far apart they are. I want to know what their difference is. So I need to be subtracting them. So p of 31 plus h minus p of 31 over h. And if we want to break this down into, like, kind of unite this to derivative, what is this really giving me? This is going to give me the instantaneous rate of change of population, where we use p prime to talk about that, p prime to talk about the derivative of p at what t value? 31. Okay, so I believe that is really as far as we can go with, finding the derivative at this point. All right, then estimate the value of this limit. So I am not going to go through that in detail, but what I will say is this. We could estimate this limit in a way very similar to the way we did, both part A and part B. So for part B, we use a 10-year span. For part A, we use a 7-year span. Those are very, very long time spans. For us, I really want to see what happens when H gets really, really small. So something I might do is this. Let's not even look at a full year. Let's look at a week. So if we look at 1 week, and we know that time is measured in years, how many weeks are there in a year? 52. So that means that H will be like 1 over 52. So maybe we could do this. We could it's still going to find an average rate of change, but you're looking at an average rate of change over a very small change in time values. So what's the population 1 week? So literally January 8th of 2024. So that'll be a time value of 31 plus 1 over 52 minus the population at time equals 31 over what? 1 over 52. So this right here would not give you the exact instantaneous rate of change, but it would give you a pretty close estimate. The last thing I want to talk about is, what are the units on this? So if we want to talk about the units of a rate of change, we really need to talk about what the two covariant quantities, what they're represented in. What's the population measured in? It's measured in billions of people. Billions of people. What is the time base measured in? That is measured in years. So any derivative we come up with for this function, any average rate of change, any instantaneous rate of change is going to be measured in the units of billions of people per year. All right, moving on to part D. Find an equation for the tangent line to the function. Okay, so we want to find the equation of the tangent line. So that's going to be, a couple of forms we could give that in. Y equals mx plus b. So slope-intercept form, or if you'd rather, we can do point slope form. So y minus y1 equals m times x minus x1. So let's start filling in these details here. I want the equation for a tangent line of the function at the point where the t-value is given by today's date. So what information do we need? Really, the y is going to come from, the y value is going to come from p of 31. The x is going to come from, well, that's our input value. That's going to be 31. So where are we going to get our slope from? So think about what slope really is. Slope is an instantaneous rate of change. So we go back to our last slide here. Our slope is going to come from basically this very small average rate of change that we found. So from this right here will give you your slope. And then from there, if you know what the population is at year 31, you have your slope and you multiply it by 31, then you can use that to find B. So I'll leave that. Hopefully that kind of gives you a push in the right direction. But I'll leave the details to you, and like anything else, please let me know if you have any questions.